In 2019, I published research on a question that had been haunting me for years. What is the opposite of blue? Depending on which colour wheel you're using, blue can be the opposite of orange, or the opposite of yellow, or somewhere in between. Is there a true opposite? Why isn't there agreement between the different colour wheels? Stay tuned to find out what I discovered and what implications it has for how I teach my students about colour. I will talk you through the problem, then we'll look at various colour wheels. Then I'll delve into the language of colour, which turns out to be a key source of the problem. And finally, the solution. Colour opposites are used to great effect in art. Here Leonard Efremov has used orange as the opposite of blue. But in this painting, Vincent van Gogh has used yellow as the opposite of blue. So which is correct? What is the opposite of blue? At primary school, you were taught this, that there are three primary colours, red, yellow and blue, that they can be mixed to make the three secondary colours, orange, green and violet. So blue is opposite orange. You'll have learnt all this at the age of between 3 and 7. But when you get to university, you come to my class, and I tell you that the world is not that simple. I show you that the three primary colours used in printers are cyan, magenta and yellow. I tell you that the three primary colours used in computer displays are red, green and blue. Your primary school teacher told you the primaries are red, yellow and blue. And because it was so long ago, and you were at a particular stage in your development, you've ingrained that red, yellow and blue must be the truth. And so me, the professor, must be wrong. I then go further and show you different colour spaces. LAB colour space has 4 principal colours. Munsell's colour space has 5 principal colours. The HSV diagram has 6 principal colours. And then the chromaticity diagram on the right here has an infinite number of colours. What's going on? How do we reconcile all these different colour spaces? And how could your primary school teacher have been so wrong? So let's go back to the red, yellow, blue primaries that you were taught at school. Where do they come from? We have known since the 17th century that you can mix red, yellow and blue to make a wide range of colours, though different artists used different shades of red, yellow and blue when doing this. This understanding of red, yellow, blue was consolidated in the mid-20th century by Johannes Itten, a Swiss artist. Itten's colour wheel has a prototypical red, prototypical yellow and prototypical blue, and he mixes these to make the 3 secondaries, green, orange and purple, and then 6 tertiary colours. Itten's colour wheel took off and is now widely used as the basis of teaching about colour theory in art schools around the world. But Itten's colour wheel is not the only colour wheel. There is a well-attested theory that the human visual system has 2 different colour signals going to the brain, one of which is red versus green, the other yellow versus blue. This is the foundation of what was called the natural colour system, developed in Sweden in the late 1960s. It has 4 principal colours, red, yellow, green and blue, but 4 principal colours is not the end of the story. Alfred Munsell, an American artist, developed the Munsell colour system in the first decade of the 20th century to help with exact specification of colours. It has 5 principal colours: yellow, red, purple, blue and green. Munsell based this on an extensive set of experiments on humans to determine what colour differences are just noticeable. He aimed that any equally sized step around his colour wheel would have the same perceptual difference to a human no matter where on the wheel it was. So seriously, how many principal colours are there? We start with red, yellow and blue from your primary school days. Then Herring's opponent colour theory says that we should have 4 principal colours. Munsell says there should be 5. The HVS system has 6 colours, the 3 printer colours, cyan, magenta and yellow, combined with the 3 display colours, red, green and blue. And then we can take Itten's primaries and secondaries to make a 6-colour wheel with red, orange, yellow, green, blue and purple. And all of these are some sort of simplification of the actual wheel, which has infinite colours. Each of these sets of principal colours has its proponents, including Isaac Newton, whose early work on the rainbow proposed 5 colours of the rainbow, the same 5 that Munsell used. Okay, we have 4 different ways to think about the colour wheel. You and I might expect that they all agree with one another, but the answer is no, they do not agree with each other. So let's look at the detail of that. The angle between yellow and red varies between 60 degrees for the printer's colour wheel to 120 degrees for the artist's colour wheel. That's quite a big difference in how far it is from red to yellow. The angle from green to blue also varies by the same amount. So the green to blue range is squished in the artist's colour wheel, it's a bit bigger in Munsell's colour wheel, bigger again in the opponent colour wheel, and it's at its biggest in the printer's colour wheel. It's as if the colour wheel is made of rubber and we stretch it in different ways. So can we get any agreement on what is the opposite of blue? No. 2 colour wheels say the opposite of blue is yellow. 2 say orange. Well, okay, what about the opposite of red? Again, no. 2 colour wheels say green is the opposite of red. 2 say cyan. So not one of these 4 wheels agrees with any other on what colours should be opposite red and blue. It is not surprising that my students get confused. How do we explain these differences? For this, we need to turn to the language of colour. How we talk about colour in English has a big impact on how we understand what is going on here. We turn to Berlin and Kay's theory of basic colour terms. Berlin and Kay's theory starts from the assumption that every language has basic colour terms that are not reducible to other colour terms. So there may be many words within a single colour category, but there is 1 or maybe 2 overarching words that describe that category. That's the word that you teach children when teaching them about colour. So in this case, these are our words in English for different shades of blue. But blue is the basic colour term. English has 11 basic colour terms: black, white, grey, red, blue, green, yellow, orange, brown, purple, pink. But how do you work out the basic colour terms in a language? Well, first you talk to native monolingual speakers. You get them to tell you what the basic colour words are through conversation. Once you have the basic colour terms, you then use a Munsell colour chart, like this, to get them to map out what colours those basic terms refer to. For example, the language of the Barinmo people has 5 fundamental colour terms that map to the Munsell chart in this way. WAP is white and pale versions of all other colours except yellow. Kel is black, but also dark versions of brown, dark yellowy greens, dark blue greens, and dark blues. It also incorporates certain shades of brighter blue purple. Mehi covers red and dark pink and reddish purples. War covers yellow and yellowish shades of green, orange and pink. And Knoll covers almost all greens and blues. English has 11 fundamental colour terms. This chart shows 8 of them. The others are white, black and grey. To create charts like that, you start with 160 carefully calibrated coloured chips. You then give native speakers tasks to categorise those chips. One task is select all of those coloured chips which you would, under any conditions, categorise as being of a particular basic colour. And this is the result you get. You can see that there are a lot of colours that English speakers would categorise as green or blue, but not so many that are unequivocally yellow or orange. The large swathes of white in this diagram are the areas where the colours shade from one to another and people cannot agree on a particular basic colour. What is interesting is that in over half the diagram, native speakers do agree with one another. Berlin and Kay set another task. out of the 160 colour chips, pick the one that is the best, most typical example of that colour category. Native speakers agree with a stunning degree of consensus. The little stars are the points that are agreed as the best, most typical example of each of the 8 basic colours. These best, most typical examples are important in understanding the language of colour wheels. So let's return to those colour wheels. Looking at the 4 colour wheels, we see that every single colour on every single colour wheel is a basic colour term in English. That is except for cyan and magenta on the printer's colour wheel. Why does that wheel have these peculiar colours, cyan and magenta? Cyan, magenta and yellow are the primary colours for printing. They're defined by the physics of light. We divide up the light spectrum into 3 chunks with long, medium and short wavelengths. Cyan reflects all the purple, blue and green light. Magenta reflects all purple, blue, orange and red light. Yellow reflects all green, yellow, orange and red light. In practice, you cannot make inks that are ideal. As you see at the bottom, we can get a pretty decent result, enough to print colour pictures that are reasonably close to reality. But because these inks are determined by the physics, the colours do not match the linguistic space. Cyan is a greeny blue. Magenta sits somewhere between pink, purple and red. So we don't teach children that the primary colours are cyan, magenta and yellow. We teach them instead that they are blue, red and yellow. It's a lie, but it's close enough to the truth that it works well enough for simple colour mixing. Okay, so that is one source of confusion. We want the primary colours to be the nice linguistic basic colours we learnt as children. But the physics does not allow that. The physics says that the primaries are cyan, magenta and yellow. You can rail all you want against that, but the physics is the physics. So that's one problem. Now for another 2 problems. When I ask what is the opposite of blue, I need to define what I mean by those words. How do we define opposite? Is it the colour diametrically opposite on the colour wheel? That's what we assumed earlier. Or is it the colour you mix with blue to make a black? That's an artistic definition. Or is it the physiological after image? That is, if you stare at a blue thing for a long time, then close your eyes, what colour do you see? Try it with a big blue object. When I do this, the after image I see is a bright orange. That's a result of the chemical and neural processes in your eyes. Any of these could be the opposite, and all 3 might give you a slightly different answer. And then there's the question of what you mean by blue. As you now know, blue in English covers a very wide range of colours, from sky to navy, from cyan to indigo. But we also know that when I say blue to you, you immediately jump to that best, most typical example. That's the blue that's pretty much right in the middle of the whole swathe of colours that we call blue. So when I say blue, I might mean any one of a very wide range of colours, but when I ask you to think of a blue, you think of this best, most typical example. Which leads us to another finding. Our colour words do not necessarily mean what we think they mean. Here are colours printed on a laser printer in the middle of the circle, and painted with colour inks in the outside ring. In both cases, we are mixing cyan, magenta and yellow, the 3 printing primaries. If we look at the colour wheel, these primaries are supposed to mix to get green, blue and red. But that's not strictly true. The blue here is actually a purplish blue. And the red here is actually an orangish red. This is another source of confusion for students. We use the shorthand words blue and red for colours that are not the most typical shades of blue and red. If we look at all of the colour wheels, we find that other wheels have the same issue. We looked at the printer's colour wheel, where blue is really purplish blue and red is really orangish red. In the CIE-LAB space, green and red are not the most typical shades, red being a purplish red and green being a cyanish green. In the Munsell colour system, the colours labelled green and blue are not the best, most typical versions of green and blue, but both a bit cyanish. Once you know this, you can work out where on those three colour wheels you would find the most typical shades of green, red and blue. And when you do that, you find that all three of these colour wheels become very similar to one another, with the angle between green and blue and the angle between red and yellow being almost identical across all three wheels. So the linguistic understanding has allowed us to reconcile these three systems to be pretty much identical. However, the NCS colour wheel and the artist colour wheel cannot be adjusted like this because their principal colours are defined based on the most typical versions of each colour. So let's look at the biggest source of confusion. Why are the printers and artists' colour wheels so different? They are both based on three primaries and on the concept of mixing paints or inks to make all other colours. Surely they should be the same. Why are they so different? The truth is that the artist's colour wheel is just a very rough approximation to the physically correct printer's colour wheel. Why is this approximation so embedded in our culture? To answer that, we go back to the linguistics. Today's colour wheel comes from Itten's work in the mid-20th century. When Itten was defining his three primaries, he did this based on the linguistic, best, most typical version of the three primary colours. He says, a person with normal vision can identify a red that is neither bluish nor yellowish, a yellow that is neither greenish nor reddish, and a blue that is neither greenish nor reddish. The primary colours must be defined with the greatest possible accuracy. But that greatest possible accuracy is with respect to things that are linguistically determined and therefore to things that are culturally determined. His definition is not based on the physics of colour. Indeed, you will see that there is a problem inherent in his very definition. Red must be neither bluish nor yellowish. Fair enough, that's defining red in terms of the other two primaries. But yellow must be neither greenish nor reddish. Green is a secondary. Why is he using it as a referent? And blue also must be neither greenish nor reddish. Itten is implicitly using Herring's theory of colour opponents with four principal colours, where red is opposite green and yellow is opposite blue, and using these to define a system with three principal colours. And then, when he defines the secondaries, he does the same thing. He wants mixes that produce the best, most typical versions of orange, violet and green. So Itten's three primaries and three secondaries are in fact determined by the culturally and linguistically agreed best, most typical versions of each colours. And there's no guarantee that those six colours are in any way related to the actual physics of colour mixing. So Itten's artists' primaries and secondaries are linguistically determined, whereas the printer's primaries are physically optimal. There's no reason why the physically optimal primaries should be the same as the linguistically determined primaries. The physically correct primaries are magenta, which sits somewhere between the linguistic red, pink and purple, yellow, which is pretty much a linguistic primary, and cyan, which sits somewhere between green and blue. You cannot be simultaneously physically correct and linguistically correct, and therefore that is why the two colour wheels are different. One is based on physics, one is based on how the human brain is programmed to think about colour by our English-speaking culture. And it is not just English. All Western European languages pretty much agree on the division of colour space and the location of the best, most typical versions of each of the 11 basic colour terms. So, does any of this matter? Yes, in two ways. First, the artist's colour wheel is the principal source for teaching about colour before high school. It gets embedded in children's brains as the correct way to think about colour. But it is at best a rough approximation to the truth. That means that it is challenging to unteach it when students need to learn colour theory in physics or in computing. Therefore, this information is important in helping educators to understand why those students have a hard time ditching their primary school concept and moving on to the more accurate colour models. Secondly, the colour wheel is firmly embedded in the art community. Artists are taught to use explicit angles on the colour wheel to make harmonious colour combinations. But that colour wheel is not the only colour wheel that might be valid, and so blindly sticking to this limits the ways in which you can combine colours in a composition. As Van Gogh showed us, the opposite of blue is not always orange. So what have we learnt? We've learnt that the artist's colour wheel leads to confusion when students meet other colour wheels that appear to contradict what they learnt in primary school. We've learnt that the source of the confusion is actually the way we use language to describe colours, and therefore we've learnt that when we are talking to students about the technicalities of colour, we need to be careful about using words that have common meanings. The words opposite, blue, red and green mean different things in different technical contexts. Thank you so much for listening. I'd love to hear your feedback. Have you had experiences where you thought that the artist's colour wheel just did not make sense? Have you wondered why printers use cyan, magenta and yellow? Have you met any of the other colour wheels before you heard this talk, and did they confuse you? Let me know in the comments, and see you next time.